Hello everyone, welcome to my YouTube channel. So today I am going to solve a problem from group theory. Okay, so consider the following statements. So the statement saying that every finite group has finitely many subgroups, every infinite group has infinitely many subgroups, every countable group has countable many subgroups, every uncountable group has uncountable many subgroups. So which of the following statements are actually correct and which are wrong? Okay, so let's start. So first one. So let G be any finite group, right? Say order of G is K. So G is actually a set. G is actually a set with G is a set of cardinality K, right? So G is a set with cardinality K and G has a separate group structure. That is different. But ultimately, first of all, G is a non-empty set and G has cardinality K, right? And what is the cardinality of power set of G? Power set of G has cardinality of 2 power K, right? So any subgroup, first of all, it is a subset, right? Any subgroup is a subset of G, first of all. So that means it is an element of power set of G. Is an element of power set of G, right? That means number of subgroup can be at most 2 power K. So number of subgroups is finite. That means any finite group has finitely many subgroups. Okay. Second one. Let G be a infinite group. Okay. If G has an element of infinite order, then we are done. Why? Then we are done. Why? Because say A belongs to G, has infinite order, and H is cyclic subgroup generated by A. That means clearly H is a subgroup of G, and any subgroup of H must be a subgroup of G, right? So any subgroup of H must be a subgroup of G. So since H is a cyclic subgroup and A has infinite order, that means H is isomorphic to Z plus, right? And we know that Z plus has infinitely many subgroups. In particular, the subgroups are looking like NZ, right? These are all the subgroups. N can be any natural number. So this will imply that H has infinitely many subgroups. H has infinitely many subgroups. And which says that G has infinitely many subgroups. Right? Because any subgroup of H must be a subgroup of G also. Right. Okay. Now if all the elements of G has finite order. Okay. Then for any G belongs to G, let Hg be the cyclic subgroup generated by G. By G, right? So first pick A belongs to G. Clearly HA not equal to G. Because A has finite order, we already assumed that. That means HA is finite because order of A and order of HA is same. So HA is finite and G is an infinite group. That means HA not equal to G. That will imply G minus HA is non-empty. Now pick B belongs to G minus HA and consider HB, right? Then HB is another subgroup, right? And continue this process. So what will be the next stage? The next stage will be pick C belongs to G minus HA union HB, okay? And continue this process. So we can do the same thing until G minus union of HAI, I belongs to some indexing set, will be empty, right? We can do the same thing. So if G minus HA1 union HA2 union HA3 union HAN is empty, that will imply G equal to union of HAI, I equal to 1 to N. Right? And each HAI is finite. That will imply G is a finite. G is finite, which is a contradiction. That means we can continue this process infinitely many times. So hence, by continuing this process, we get infinitely many subgroups. Okay, right. So that means every infinite group has infinitely many subgroups. Now I'll do third option later. First let me do fourth option because third option is slightly tricky and more interesting. Okay, so the fourth option says that every uncountable group has uncountable many subgroups. Okay, so this is also true and we can prove it the similar way we have done for this infinite case. Okay, so let G be an uncountable group. We need to show that G has uncountable many subgroups. So the same process. Let A belongs to G. HA would be subgroup generated by A. So HA is finite or countably infinite. Okay. So it is finite or countably infinite. Finite or countably infinite. Right? That means this is non-empty because G is uncountable and HA is at most countably infinite. So this is non-empty. So choose B belongs to G minus HA. Okay. Then consider HB. This is also finite or countably infinite depending on the order of B. Again continue this process. Okay. So if G minus union of HAI, I equal to 1 to infinity is empty. Okay. That means if in this process we end up with countably many subgroups, then this must be empty because until it becomes empty, we will continue this same process, right? So then this will imply G equal to union of I equal to 1 to infinity HAI, right? And we know this is a basic set theoretic result. Countable union of countable sets is countable. Right? This is the basic set theoretic result. So countable union of countable sets is countable. This will imply that G is countable. because each HAI is at most countable, and we are taking countably many union, so G becomes countable, which is a contradiction because we start with a group with uncountable cardinality, right? Hence G must have uncountable many subgroups. Okay, now the most interesting part. Okay, so we get that the first one is correct, second one is correct, fourth one is correct, but the third one will not be correct. Okay, and there is a special example, that a countable group with uncountable many subgroups. Okay, so special example, that Q plus rational number with addition is a countable group, because we know that Q is countable with uncountable many subgroups. So let me explain how we get uncountable many subgroups of this group Q plus. Okay, so first we know that there are infinitely many prime numbers, right? Let S be the set of all primes, right? Since S is infinite, okay, PS, which is power set of S, is uncountable. Okay, okay. Now for any subset X of this S, okay, that means X belongs to power set of S, we define Hx, okay, which is and so we are considering a set Hx which is A by B belongs to Q, that rational numbers such that GCD of AB is 1 and every prime factor of B is contained in S, not S, sorry, X. Okay, because X is a subset of S, that means say X is 2 3 5, or maybe X is 3 7 11 19, anything. Okay, or X is 3 7 23 37, this, anything. So we are defining this Hx. So first claim is Hx is a subgroup. First claim, Hx is a subgroup, which is very easy to check because A1 by B1 belongs to Hx and A2 by B2 belongs to Hx. This implies A1 by B1 plus A2 by B2, which is same as A1 B2 plus A2 B1 by B1 B2. Now all the prime factors of B1 is contained in X, all the prime factors of B2 is contained in X, that means all the prime factor of B1 times B2 product is also contained in X. So that means this is in Hx. And inverse is also there, because you can write the inverse is minus A1 by B1, right? So already all the prime factors of B1 is already in X, right? And you can write 0 to B 0 to be 0 by P, where P belongs to X. That's why our identity is also there. Hence Hx is a subgroup. Now the interesting claim is that second claim, Hx equal to Hy if and only if X equal to Y. So we can easily see if X equal to Y, then Hx equal to Hy from definition. It is from the definition. Now if Hx equal to Hy, now if X not equal to Y, it is easy to see, like say if X not equal to Y, so if X not equal to Y, then choose a prime P belongs to X but P doesn't belongs to Y, or you can choose some other Q belongs to Y who doesn't belong to X, anything. Okay, then by construction 1 by P belongs to Hx, because 1 by P is of the form A by B, where B is P, so that means B has the prime factorization P, the P itself, and P is already in X, but P is not in Y. That means 1 by P doesn't belongs to H of Y, right? So hence Hx not equal to Hy. That means if X not equal to Y, then Hx not equal to Hy, and X equal to Y implies Hx equal to Hy. Hence we get Hx equal to Hy if and only if X equal to Y. Now consider set of all subgroups of Q plus. Okay, let that set is T, and so define a map psi from power set of S, that is power set of all primes, to T, that any X goes to Hx. So by our construction, by our proof, by our above claims, psi is injective, right? And power set of S is uncountable. That will imply T is uncountable. There are many other subgroups of Q plus, but these are already uncountable many subgroups of Q plus. That means this collection must be uncountable, because we have already shown there are uncountable many members in the collection of all subgroups of Q plus. That's why T is uncountable. Okay, so hence only this third one is wrong. It's a very interesting problem. Hope you can understand it. If you have any doubt, just comment below.